So we have completed till here. Have you all written it? Yes, have you written it or not till here? Or were you supposed to write? Yes, Ali, Ubaidullah. In the last class, till where have you completed? Audible?
I was absent last month.
Oh, Ubaidullah was absent. Ali, you tell me, you were there?
Yes, ma'am, we wrote this.
You have written this. So answer, Ali. Okay, so coming to Maxwell's displacement current. See, what did Maxwell do? Okay, yes, I remember we had to start from Maxwell's displacement. Let's complete the chapter today. More or less, it will be completed. See, what did he do? We had studied the concept of Ampere's circuital law. He took two loops. This is one loop, let's say C1, and he took another loop here, that is C2. Two just closed loops he took. Now this is a battery that is connected. This is a key that is connected, and current is flowing through it. Okay, current is flowing through the circuit like this. Now, if I C means closed loop, C1 and C2 are basically closed loops present. Closed loops are C1 and C2. Now, see at C1, when he applied the Ampere circuital law, line integral of magnetic field, this is equal to mu naught times the current. This is as it is present because current is actually flowing through the circuit. But when he took the loop between the capacitors, okay, these two are the plates. So between the capacitor plates, a loop is taken. Now we know one thing already, that in capacitors, current does not flow between them because it's a dielectric material. How will the charges be transferred? Charges are basically transferred by the process of induction. If this is positively charged, this makes it negatively charged, and that's how the further charges are transferred. So same is the case here as well. So in between, if I take a loop over here, that is if I take this closed loop, so B dot dl's integral, if I take, it will be mu naught times current, which is 0. That is 0. So this is, there is there is a discrepancy between the closed loop 1 and closed loop 2, right? These loops, they are not these the closed loop 1 and closed loop 2. These loops are giving the different values. It means Ampere's circuital law is inconsistent. If it is consistent, then every time, everywhere, it should give you the correct answer. But here in between, it's coming 0. Either Ampere's circuital law is incorrect, or something was there which Maxwell was doing incorrectly. But when you look at the Ampere's circuital law and the experimental history behind it, that's absolutely right. Means something was there which he couldn't see, and because of which the entire value or the equation of Ampere's circuital law was coming incorrect. So this result of Maxwell was inconsistent with the Ampere circuital law. Okay, that was the first thing that came when all of this occurred. So he realized that one is the current that is flowing in the circuit. That current which is flowing in the circuit, see, basically two kinds of currents are there. One current is the conduction current. One current is the conduction current. Conduction current means the current that is flowing in the circuit because of the discharging of the battery. From the battery, the current that is coming, that is your conduction current. Okay. But he said, Maxwell said that there is not just a single current which we are able to see, which we are able to observe. There is one more current which is present between the capacitor plates. That is known as the displacement current. This is known as the displacement current, represented through ID, displacement. So this is the conduction current, this is the displacement current. Now, what is the story behind it? Basically, see, when we have the magnetic field getting changed, what did we study in the entire chapter, EMI chapter? That magnetic field can lead to current. This is what we studied throughout. that yes, current carrying conductor will produce the current like this. Magnetic field is there. Whenever we just saw the Faraday's experiments also, that bar magnet was brought closer to the coil. So magnetic field lines came. When the magnetic field lines came, this gave rise to the deflection in the galvanometer. That confirmed the point that yes, magnetic field can also produce current. This we have already done in EMI chapter in detail. Now see, electromagnetic waves, there is not just single magnetic field present. There is a component of electric field also existing, equally taking part. So whatever current is produced due to this electric field change, that is, here also another current is produced. See why? Between the capacitor plates, this is positively charged, this is negatively charged. In between them, electric field will be existing. Now, in this chapter, we have studied time varying. All these magnetic field and electric field, these are time varying. Okay, so these are time varying electric field and magnetic field. They are fluctuating with time. A change in the magnetic field will produce a change in current, and a current, that is our conduction current. And this change in electric field will produce a displacement current. That is what the displacement current is about. It is that current that comes into existence in addition to the conduction current. Whenever electric field and flux, this is referring to the electric field and the electric flux change with time. Am I clear till here? Ali and Ubaidullah? Till here, have
Yes,
you
ma'am.
understood? Okay. Consistency part we'll discuss later. First, copy till here. Then we'll continue. How was this displacement current proved? Current was proven that yes, it was right. Okay, see, let's continue, Ali and Ubaidullah. I hope you have written or not? Yes, Ubaidullah, Ali.
Yes.
See, when we write the Maxwell's current, or before that, the displacement current has the formula epsilon naught d phi over dt. Now you know what is d phi over dt. That's the rate of change of flux, and this is the permittivity. Okay, this is the rate of change of flux. This is the rate of change of flux, while this is the permittivity. Permittivity. And ID is the displacement current. Okay, this is the displacement current that is present. Now, see, basically the entire equation that we have. See, he said in the loop 2, C2, B dot dl integral is mu naught times the current enclosed, that is 0. Because there was no current between the capacitor plates, but now we know between the capacitor plates there is this displacement current. So it will be ID into the displacement current. That is, if I put the values, let's check now. See, if I talk about this ID, whether it's right or wrong, this is mu naught. If ID is correct, then this should be epsilon naught d phi over dt here, right? According to Gauss law class, flux is what? Charge by permittivity. So if I put that dq over dt, and this epsilon naught will come out. Epsilon naught will get cancelled. What is dq over dt? That's current. So it's proven. This is basically the current. So now you can say B dot dl's integral is still equal to mu naught I. Now this is matching. For the loop C2 also this is matching. Now there is a consistency in the Ampere-Circuital law. There is the consistency in Ampere-Circuital law which was missing before. So you can see here the value, you can write the equation as integral of V dot dl is equal to mu naught times epsilon naught d phi over dt. This also you can write, or any other value. Now see, we basically say modified Ampere-Circuital law. If you remember in one of your magnetics test, I gave modified Ampere-Circuital law, and I told you also that is not the one which we've already studied. Ampere-Circuital law. So see, modified is different. In modified, we'll say B dot dl's integral is mu naught times the conduction current plus the displacement current. Okay, this is the modified Ampere-Circuital law, which you can say integral of V dot dl is mu naught times conduction current plus epsilon naught d phi over dt. This is it. Okay. So properties we'll see, and then the numericals. Okay, that's it. It will cover the chapter. It will end it. Please write it from here. Is it clear? How is it consistent? Is the derivation clear? You have it comes in the exam to prove. Is it clear or not?
Yes.
Okay. Please write it from here. Well, Sahi, you better not.
Yes, ma'am.
Okay, let's come to the properties. Four properties are there, very easy. First is what you already know, that whenever there will be a change in the electric flux, that will lead to the formation of a displacement current, which is there. Now, see, this displacement current can be a cause of producing magnetic field also. Like your usual current, which that current produces a magnetic field. This concept we studied in the Biot-Savart law. This whole concept we studied in the Biot-Savart law. So, same thing, displacement current can also produce a certain amount of magnetic field. Now, displacement current is directly proportional to the magnitude of the charge. Greater the charge, greater the current. Lesser the charge, lesser the current. Last is it satisfies the property of continuity. Means class, see, earlier what did we have? The whole concept was, let's say this is a capacitor plate connected to the circuit. So basically it was said that the current flowed till here and through here like this, and there was no involvement of current between the capacitor plates, right? Now it says this whole after Maxwell's theory, there's a continuity in between the plates. Also, a current is flowing. So a complete circuit with full movement of current is flowing in it. Clear? These are four basic properties. Write it so that we can discuss the numericals. Write it down from here. Done?
Last. Ma'am, last point I'm not able to understand.
Third one or fourth one?
Third one.
Third one is C. Magnitude of displacement current is equal to rate of displacement of charge from one capacitor plate to another. Means if lots of charges they move from one plate to another, displacement current will be more. But if less number of charges flow, less current will be produced. That's what has been said, that the magnitude of the charge will determine the magnitude of the current. Okay?
Yes, ma'am.
Now done.
Yes, ma'am.
Let's practice some questions now. This says a parallel plate capacitor has circular plates, each of radius 5 centimeter. Radius of the plate. This is given as 5 centimeter. It is being charged so that electric field in the gap between its plate rises steadily at the rate of 10 to the power 12 volt per meter per second. This is not electric field, it's the rate of electric field, dE over dt, that is 10 to the power 12 volt per meter for electric field per second for the rate. This is not just electric field, it's what is the displacement current. See, for the displacement current, we know this is equal to epsilon naught d phi over dt. Now, what is flux equal to? Flux is equal to electric field into area. Correct? So put it here. This will be epsilon naught. If you put it over here, this will be epsilon naught d EA over dt. So this is equal to epsilon naught. A will be taken out. dE over dt will be left. Now, since the radius has been given, we can calculate the area as pi r square, which is equal to pi 5 into 10 to the power minus 2 whole square meter square. That's the area. So epsilon naught, area, dE over dt. Dt is given, so ID will be given by, this will be given by, the ID can be calculated as epsilon naught is 8.85 into 10 to the power minus 12. Area is pi into 5 into 10 to the power minus 25 into 10 to the power minus 4 into dE over dt is 10 to the power 12. So this much you can solve. Whatever answer comes in ampere only, that will be the displacement current. Okay, write it. Then we'll do one more question based on this. First, write it till here. And just text me done once both of you have written.
Ma'am, how is phi equal to E?
Electric flux, formula of electric flux, E dot A.
Was it done in yesterday's class?
Electric flux, Ubaidullah. First chapter. Electric flux, number of electric field lines crossing area perpendicularly. What happened? Gauss law. Electric flux is equal
Yes,
to
ma'am.
charge by epsilon naught. Now recalled.
Yes.
Done?
Yes, ma'am.
Okay. See, let's move on to the next question. See, this is the voltage between the plates of a parallel plate capacitor of capacitance 1 microfarad is charging at the rate of 5 volt per second. Rate of electric field is given. No, rate of voltage is given and capacitance is given. C class. When we have the current as from here epsilon naught d phi over dt, this is the displacement current. Now, if we use the Ohm's law from here, V is not Ohm's law, sorry, capacitance's equation. From here, if I use the equation of the capacitance, this is what is the value of the displacement current and what are you provided with? Voltage, you provided with the voltage and you provided with the capacitance. So C and V are there. So C, current, basically this is C d V over dt. You can use this formula C t V over dt. But how? Look, if we have current, current is equal to dq over dt. Now charge, is capacitance into voltage. Because you don't have the flux with you. If you have no information, you cannot use this formula. Only epsilon naught is known to you. In fact, the time is also not known to you. So how will you calculate the current? So this formula is not the right choice. Put this here. So current is equal to d CV over dt. From here, capacitance will be taken out, dV over dt will be left. This is important formula also. You can use it directly since it is coming in this question. So I have discussed it in this manner. Now capacitance is 1 microfarad 10 to the power minus 6. Voltage is 5, right? So current is basically 5 into 10 to the power minus 6 ampere. This is the answer, which is your displacement current. Use this. This is the most important thing in this question, which I wanted to discuss. Write it. We'll see some other questions as well. Okay, see, this says that a parallel plate capacitor has two metal plates of size 30 centimeter into 15 centimeter. So area is given as 30 into 15 into 10 to the power minus 4 meter square, and separated by 2 millimeter. Means distance is given as 2 into 10 to the power minus 3 meter. If this capacitor is being charged, so that charging current has a steady value of 100 milliamperes. Current is 100 milliampere, 10 to the power minus 3. Okay, and it says calculate the rate of change of potential difference between the capacitors. You have to find out what's dV over dt given, right? Rate of change of potential difference between the capacitor plates. See class, use the formula I is equal to C dV over dt only. But for capacitance, don't leave it like this. For capacitance, use it epsilon naught A by D. That is 8.85 into 10 to the power minus 12. Area is 30 into 15 into 10 to the power minus 4 divided by 2 into 10 to the power minus 3. This will be the capacitance, this much of farad, right? So current is also given. So what will be the voltage? dV over dt will be simply calculated by current divided by the capacitance. So this whole term 8.85 into 10 to the power minus 12 into 30 into 15 into 10 to the power minus 4 by 2 into 10 to the power minus 3 into the capacitance will be the current will be 100 into 10 to the power minus 3. 100 into 10 to the power minus, no, current is 100 into 10 to the power minus, it will be multiplied, not divided, because current is 100. So into, what was it? 100 milliampere. So 10 to the power, what was it? Minus 1. Minus 1. This much will be volt per second. Use the same formula. It's just that for capacitance, use epsilon naught A by. Okay. One more question we'll see. First, write it. Write down this one. Have you noted the question, or just is it left to be written?
We wrote.
You have written? Okay. Ali, you too?
Yes, ma'am.
And
Yes.
question above is from your dual nature chapter. So that time we'll discuss. Let's discuss this question. So magnetic field is given to us. Let me rewrite this equation. This is By is equal to 12 into 10 to the power minus 8 sine 1.2 into 10 to the power 7z plus this is 3.6 into 10 to the power 15t. This much is the value. Now you should know the actual equation also, which we use. P is equal to V naught sine kz plus omega t. We have already discussed this equation. It says calculate the energy associated with the wave energy density. Now B naught you already know, 12 into 10 to the power minus 8 minus 80 you know. So 12 into 10 to the power minus 8 Tesla. Okay. Now, E naught is also needed for current density. In the last class only we have done that. So for E naught, this can be calculated. We know the speed of light into the magnetic, the speed of light is equal to electric fields peak value and the magnetic fields. So E naught will be equal to C into B naught, that is 3 into 10 to the power minus 8 plus 8 multiply to B naught is 12 into 10 to the power minus 8. So this will calculate. This is equal to 36 Newton per Coulomb, the electric field. Now you have it for the first part when you have to calculate the total energy density. For peak value, I have told you use 1 by 4. If it is RMS value, then we use 1 by 2. So 1 by 4 E naught square into epsilon naught plus 1 by 4 B naught square divided by mu naught. Values you can put, in fact, you can take 1 by 4 out. E naught square will be 36 square into 8.85 into 10 to the power minus 12 plus B naught square is 12 into 10 to the power minus 8 whole square by 4 into 3.14 into 4.10 to the power minus 7. So this you can solve and see whatever is it, that will be the energy density. Joules per meter cube you write because energy density is actually energy per unit volume. Second part says speed of wave. For the speed of wave, you should know the frequency multiplied to the wavelength. Okay, now wavelength and frequency, how will we calculate? See, k is equal to 2 pi by lambda and lambda is equal to 2 pi by k. So lambda is equal to 2 pi. Now k is given as, see this kz, 1.2 into 10 to the power 7, 1.2 into 10 to the power 7. So this much of it, this much meter will be the wavelength. And what about the frequency then? Frequency is equal to omega by 2 pi, omega by 2 pi. So frequency omega is also given in the question. 3.6 into 10 to the power 15. 3.6 into 10 to the power 15 by 2 pi. This much of hertz. So speed will be basically the product of these two. You can say this is 2 pi by 1.2 into 10 to the power 7 into 3.6 into 10 to the power 15 by 2 pi. 2 pi will be cancelled. Speed will be 36 into 10 to the power 15 by 12 into 10 to the power 7. This is 3 into 10 to the power 8 meter per second, which is actually the speed of light. But that's a coincidence, any value can come. All right, please write down this question as well. That completes with EM waves. Spectrum part is left. that you have to remember by yourself, though I'll discuss in 5 to 10 minutes in the next class also. But first, please write this. Okay, Ubaidullah and Ali, you can leave. The chapter is done. I'll just discuss the electromagnetic spectrum once briefly. That will just take 10 minutes. And in the next class, I'll start with ray optics class. Okay. All right then. Thank you.
Ma'am, last one.